Today we're going to take a look at another z-test. The last z-test we did was a z-test for the mean. Actually, all we've done so far with hypothesis testing are tests for the mean. We had a z-test for the mean. Today we're going to look at a z-test for a proportion. Just a little recall, a proportion is the same as a percentage of the population. So oftentimes, we saw this with the confidence intervals, oftentimes we were given a percentage to look at instead of being told a specific proportion, like 50 out of 85 or something like that. We were given a percent more times than not. So just a little recall there, not necessarily something you have to write down. Hypothesis test involving our population proportion. Again, we're changing gears to a proportion from our mean we've been working with. Can be considered a binomial experiment when we have only two outcomes and the probability of success does not change from trial to trial. So what we are going to assume, I would just pause, I wouldn't write this piece right here. What we are going to assume when we're testing a proportion, we're going to assume the sample is random. We are going to assume the conditions for a binomial experiment are satisfied. Again, we don't get to do the actual research piece. We get, here's the information. We assume that these things have happened. We assume the sample's random, the conditions for the binomial were met, and n times p, remember n is our sample size, p is our population proportion, or population percent also. So sample size times our population proportion, greater than or equal to 5. And you have an n times q. Remember, q would just be our probability or our proportion of failure versus success. So p would be our proportion for our successes. So how many objects in our trial possess the characteristics that we are interested in. And then q would be your probability or your proportion of failure, which would be how many objects in our study or our sample do not possess the characteristic that we're interested in. So if it were me, if I was writing these down, I would just do the big number pieces. I would not take the time. We've probably written the conditions for the binomial experiment. This would probably be at least our third or fourth time. So if you need to reference those, you can definitely find those in your text. I wouldn't take the time to write all those today. Our formula. Our formula contains variables that we are already familiar with, courtesy of our confidence intervals from our last unit. It is a z-test, so we do see z equals. Remember, the p with the little, it looks like a little up arrow over it. Remember, this is, I know most of you liked this last unit. It is p hat. And that's our sample proportion. The capital X, remember, that is how many objects in our sample actually possess the characteristic that we are interested in studying. The n is our sample size. The p without the hat, that's the population proportion. That will be what we are given. It's typically given to us in a percent form. Again, n your sample size, and to find q, we just do 1 minus p. Or if you want to also make the little side note, just a little recall, p plus q will equal 1. Since at this point we should be somewhat familiar with the steps of hypothesis testing, I'm going to go ahead and dig right into our examples. We have the percentage of physicians who are women is 27.9%. In a survey of physicians employed by a large university health system, 45 of 120 randomly selected physicians are women. Is there sufficient evidence at the 0.05 level of significance to conclude that the proportion of women physicians at the university health system exceeds 27.9%? We start off, as usual, with our hypotheses. Now we have to slow ourselves down though. I know we're so used to putting the mu there, but we're no longer being asked for the mean. Couple keywords to look for. we're given the percentage, and then it specifically asks us if we can conclude that the proportion. So a couple keys to look for. You might not see a percentage. You also might not see the word proportion. You might just see one or the other. You won't always see both in each case. So since we're dealing with a proportion or percentage, whichever one, it's kind of nice that it's just P that stands for proportion. There's no hat on it because we're talking about the population proportion. All right, so we have to take a look at which one is actually our hypothesized population proportion. And just like with the mean, I think it's sometimes easier to pick out and say, well, here's the survey, here's my sample proportion. So the other piece that I'm given, that means that my percent is my population proportion. Remember from our confidence intervals when we worked with proportions, when we had percents, we had to change them to decimals before we could work with them. So same thing here. For the alternative hypothesis, it looks like we want to exceed. So exceed, we're going to go greater than our hypothesized proportion. And that is also what our researcher is trying to conclude, is what they're trying to show is that it's greater than. So that's also my claim. Before I can continue on to step 2, I have to take a little pause here and figure out if we're doing traditional method or p-value method. It makes or breaks what you're going to do in step 2. And I know we talked about it yesterday, but I just want to refresh you on, if I don't specifically say to find the p-value, I want you to just do the traditional method. So if you take a read through the question, nowhere do I state in there, let's use the p-value, so we're going to go traditional. Step 2 for traditional is to find critical values. When I go to find critical values, I like to make myself a little list of what my significance level is, which is my alpha. And I also like to jot down what type of test I have. That helps me figure out where my critical value should be, and it helps me find it a little easier. To also help me find critical values, I like to draw my sketch of the distribution. It's a z-test, so we're dealing with our standard normal distribution, just like our z-test for the mean. It's right-tailed. Alpha, remember, is the area that's shaded. It's the area in the tail. The critical value is the z-value we're trying to find. That's the cutoff between here's where we don't reject and here's where we do. It is up to you. This one's a right-tailed test. It's a right-tailed test. So just take a minute and see what you come up with for critical value. Using calculator or table E, doesn't matter. I think I have more people converting to calculator, which, hey, fantastic. So make sure you can find your critical value. All right, so our critical value should come out to be, now this is one that we saw when we did our confidence intervals. If you use the calculator, you would say, Miss Golly, I got 1.64. If you use the table E, you get 1.65. That 1/100th difference isn't going to make or break us when we're trying to determine if we're going to reject or not. It should. Now, if your test value happens to be super close to that, then it could. But typically, we're not going to see that. So we have our critical value of 1.65. Step 3 for the traditional methods, we find our test value. Z equals, and actually, wait, let me back that up a little bit here. Let's make a little list of everything we need. We need P hat, we need P, we need Q, and we need N. Now, I know for some of you, you just like to grab right from the question and pop things into the formula. That's fine. I like to make sure, especially when I have two variables, that look so close. I have a P hat and a P. So I like to write out what they specifically are, so I lessen my chance of making a mistake when I substitute in the formula. So P hat is our sample proportion. That's our 45 out of 120 of our selected physicians. Now, if that comes out to be, if we put that in our calculator, this one nicely comes out to be 0.375. That one's pretty convenient. I like that one. Remember though, dealing with our proportions, if the decimal does not terminate, so if it's not nice like this, 0.375, no rounding, you have to keep your fraction. If you cannot round on these. P is our population proportion. Q, 1 minus P. 0. And then N is our sample size, which we have 120 physicians that were selected. Again, I just like to make the list. You wouldn't have to. All this information I pulled straight from the question, with the exception of Q. I had to do 1 minus P to get that. Q is not right in the question. So now let's go ahead and substitute in. We have P hat minus P divided by, and again we have a large radical, aka square root, P times Q divided by our sample size of 120. Just double check. I know for some of us, when we have a formula and it involves a fraction, especially a larger numerator and denominator, take a minute, make sure that you can come up with, I came up with roughly 2.34. To reject or not reject? That's the question for step 4. So my test value of 2.34, this is why I like to draw the diagram out. I know that's going to fall somewhere over here. I know it's going to fall somewhere over on that right-hand side of my distribution. It falls in that shaded region. So if my test value is in my shaded region, that's when I reject. And you can go ahead and abbreviate null hypothesis as H sub 0. I'll know exactly what you're talking about. So if I get to reject the null, if I reject the null, I get to support my claim because the claim is in the alternative. So if I reject the null, I get to support the claim that's in the alternative. So there is enough evidence to support the claim that the proportion of women physicians exceeds 27.9%. And yes, you do have to state all that. It's not just good enough that there's enough evidence to support the claim. Well, what was your claim? What was your claim? We want to be specific. We want that nice complete sentence there. I do also want to make sure today, our second example, our final example. So let's take a look at our second example. I wanted to make sure I did one like this. Kind of skipping ahead to the end here. I want to make sure we did one with the p-value method. So if we take a read through our question, we have 51.7% of homes in the United States were heated by natural gas. We have a random sample of 200 homes, and we found that 115 were heated by natural gas. Does the evidence support the claim or has the percentage changed? And we are explicitly told, use p-value. Our first step, no matter which method we're using, traditional or p-value, is to state our hypotheses and identify our claim. All right. So we have our H's. Now, for this question, I know, come test time, you guys know I mix everything up. So I have to know why I'm putting the symbol I am in my hypotheses. When I read through the question, I didn't say, and I didn't read, the word proportion once. So how do I know this is a proportion question? Percent. We're given a percent here. And then we also have, does it support the claim or has the percentage changed? So proportion or percentage, those two things are going to be interchangeable for us. So we use P. For what we're hypothesizing is 0.517, so 51.7%. And then all the question says, does it support the claim or has the percentage changed? It doesn't say anywhere in the question, has the percentage increased, decreased, gone up, gone down, anything like that. So all we can do is an equal, not equal. Now, where we put the claim, we talked about this yesterday. I know some of us have a tendency to try to memorize what's going to happen every single time. Where the claim's going to go totally depends on what the researcher is actually looking to show. Typically, that's the alternative hypothesis, but not always. So we want to know, does the evidence support the claim or has the percentage changed? So we're trying to claim that the percent is 51.7%. If it changed, the change part would be the alternative with the not equal, that it's something different. Remember, the not equal to just means it's something different. We don't know increase or decrease, just something different. Since we're doing p-value method, with p-value method, some people really come to like that method better because you don't have to find critical values. But you still do have to find your test value. So I'm going to go ahead and list out, once again, all the things we need. P-hat, remember, comes to us from our sample. 115 out of 200. And we are lucky. We get a nice decimal again. You can use the fraction. You just can't round. So whatever's easiest for you to deal with the formula. For P, we have our hypothesized percentage, aka proportion. And then our sample size, we had 200 homes. Now, listing all those things out, again, guys, that's totally up to you. You want to jump right into the formula, pulling the stuff right from the question, putting it in? That's fine. It's up to you. This makes it easier for me. So we have Z equals P hat minus P divided by square root of P times Q divided by our sample size. And we should get roughly 1.64. Here's where you have to be careful. The test value in this is one of the big reasons why I chose this question. This is a test value, not a critical value. I know we just had a critical value, or if you did the calculator, you had a critical value of 1.64 in the last example. This is not a critical value, it's a test value. It's not often that they actually match, but we do need to distinguish between the two. So we can draw a sketch. Here's where our test value falls. And we have a two-tailed test. So really we'd have 1 over at negative 1.64 as well, since it's two-tailed. Now to find your p-value, remember P stands for probability. Probability is represented by the area under the curve. So to find my p-value, I need to find the areas in those tails. That's how I'm going to get my p-value. P-value is an area. So you have a couple options. You can go to the calculator, or let me show you the table. So this would be table E. Now let me show you, and I know it's kind of small up here, so if you are a table person, have table E in front of you. If I look at my test value, 1.64, if I look at my test value of 1.64, I get an area of 0.9495. But here's what we have to remember. When we look that up, here's what we have to remember. The 0.9495 is the area to the left of this value. I don't want the area to the left. I need the area to the right. So this area is 1 minus what we found in the table of 0.9495. So this area is 0.0505. Now, could you also have, if you wanted to shortcut things, could you have looked up negative 1.64 in the table? Yes. And gotten the area in the other tail. The only issue is the test value we got was actually the positive 1.64 over on the right side. So most people are going to want to look up that positive 1.64. The area you get, though, is the area to the left. I need the area to the right in that tail piece. So I have to do 1 minus. Now the p-value represents the total area. So I have to double that 0.0505. So again, p-value, P stands for probability. Probability is the area under the curve. So this is a situation where we know Z and we want to find the area. I know recently our focus has been more on I know the area, now find Z, and that's what we have to do for critical values. It's the same now for p-value, we reverse it again. I know Z, I want the area. So now you're thinking, okay, Miss Galley, so how then do I know to reject or not reject? Now we have to compare alpha with that p-value. P-value is an area, alpha is an area. Our alpha is 0.05, and I have to split it amongst the two tails. So when I do that, I get 0.025. I get the little area, a smaller area in the tail shaded in. So again, this is our alpha divided by 2. We have to split it amongst the two tails. If your p-value, my area for my p-value is in green, if the p-value area is larger than the area for alpha, we don't reject. If your p-value area is larger than the alpha, we don't reject. If your p-value area is smaller than or equal to your alpha, then you do reject. Now I know for some of you, I know the visual helps. For others of you, like Miss Guy, I'm just going to memorize this because there's only two different situations. If p-value is greater than alpha, I do not reject. If it is less than or equal to alpha, that's when I reject. So it's up to you. The sketch isn't too bad. I like drawing the sketch to really try to hit home the idea that the p-value is an area, alpha is an area. We're dealing strictly with the tails of the distribution, whether it's two-tail, right tail, or left tail. You're dealing strictly with the tails of the distribution. So now we need our conclusion. We did not reject the null hypothesis. I didn't reject it. So that means I didn't reject my claim. I didn't reject my claim. So there is not enough evidence to reject the claim that 51.7% of homes in the U.S. were heated by natural gas. So remember, I know we've been focusing a lot on that number 5. And I know some are like, Miss Golly, wait, whoa, why are you talking reject and there, not support? If your claim is the null, which is what we have, when I state my summary, it's all about enough evidence to reject or not enough evidence to reject. If your claim is in the alternative, then it's enough evidence to support or not enough evidence to support. So it's all about where your claim is. It's all about where the claim is. So let me finish today by showing you where to find this on your calculator. Go to Stat, and I'll just do this for the last example. Tests. And now if you haven't been using the calculator to this point for the hypothesis testing, just a little quick recap of where you can find the test for the means that we have been testing. Number 1 up there, the z-test. That's a z-test for a mean. That's z-test for the mean. We know the population standard deviation. Option 2 is our t-test for the mean. That's when we only know sample standard deviation. Now, it'd be an ideal world if number 3 is exactly what we needed for proportions, but it's not. It's number 5, a 1 proportion z-test. 1 proportion z-test. P is 0.517. It's our 51.7%. The X, that's how many items in our sample possess the characteristic we are interested in. N is your sample size. We have the two-tailed test. And we calculate. Now, what this will give you, I just want to make sure I emphasize this. The Z that's given to you by the calculator, that's your test value. That is not your critical value. The p-value that you're given, and I want to make sure, because I know we're dealing with p as our variable. So let me just label up here for you. This right here, this is p as in our population proportion. This z, that's our test value, not critical value. This p is our p-value. So with this particular test, we have to be very careful that the little lowercase p the calculator gives us is our p-value, not our population proportion. The calculator is not going to change that. So our population proportion was the 0.517. So just be careful when using the calculator for p-value with proportions. The calculator, though, I know I talked about this, especially with our t-test for the mean. The calculator makes finding the p-value a lot simpler than going to the table. And our table it's not as accurate, I shouldn't say accurate, it's not as precise, would be a better word, as our calculator can be. So I would, if it were me, I would be familiarizing myself with the calculator just to simplify finding p-values and just get the busy work of the test value done for you. You don't have to worry about entering that big ugly fraction in your calculator with that radical in the denominator. That's what I would start playing around with if you haven't tried it out already. So our steps haven't changed. Traditional method, p-value method, the steps haven't changed. What has changed for us? We now have p instead of mu. We're looking at a proportion instead of a mean. And our formula for our test value. Everything else is the same. How we decide to reject or not, how we find p-values, how we find critical values, and how we state our conclusion. None of that has changed.